Okay, so it seems we can be heard. So welcome again, and I hope everybody agrees to be recorded. And we have an Imperial College session. The first speaker is Sergei Chernyshenko, and he will speak about bounding time averages. Please.
Thank you, Paula. Okay, it's sometimes difficult to start a talk, and well, this is difficult because this talk is somewhat different from what usually I would give, kind of a big overview of all the entire picture and everything. But well, a couple of years already, I am obsessed with one particular problem. And what I am going to talk about is eventually this problem. But I will try to do it in such a way that now it is not working. Come on. What's going on? Okay, that's what I am going to structure the talk like. I will give some introduction, hopefully so that everyone will be able to understand what it is all about and the problem and everything. But then I will go into more and more technical stuff in the end, hopefully giving something new for everyone. And also, because this time I am not going into extensive review of work of everyone, I am sorry if I am not citing someone, but this talk, the slides, will be available online shortly after the talk. And all the links there are clickable. Moreover, here there are some links to other presentations which I did earlier, which are more extensive, with references, with everything. And you can click your way through everything. So if, as a result of this, you become interested in the problem, well, please just go there and click your way through the proper review. Well, and I will start with one single slide about the motivation, why I am obsessed with this type of thing. And that's because, well, I always was obsessed with the problem of turbulence. One needs, however, to realize that there are many ways people define what that problem is. And for different people, it's different. However, for me, it's like this. That picture on top is the instantaneous visualization of the flow, of turbulent flow in a plane channel. And it was calculated numerically. If you start zooming in, section by section, as it is shown in those blow-ups there, you will see more and more detail, huge amount of detail. And all those details were carefully resolved in the calculation at every time step. That requires a very large effort. But then, well, actually, in practice, we don't need to know all those details. All we need to know is usually just, well, lift, drag, maybe intensity of noise, 1 or 2 averaged quantities, and that's it, all that is required. And so when we are presented with something like this 260 million CPU hours, it seems to be a bit of a large price to pay for one single value. It's this picture, that's for me what the turbulence problem is. You know, I want a glass of milk, they say, okay, buy the farm, buy all the cows, and you will have your glass of milk. But I don't need the cows, and I do not want to pay the price. So the problem of turbulence, how it was understood from the very beginning, is exactly that, the problem of how to find, to buy what we need without paying for all the rest. And that problem obviously cannot be resolved by computers because, well, however powerful computer is, I will invent even more complicated problem, just add geometry, add physical effects, go to Vlasov equations instead of Navier-Stokes. That's there forever. How to do this? Well, there is one step which can be done along those lines. And that is a step back. Actually, we do not need to know the value itself. If we have bounds, two values below and above, that actually should be enough practically, as far as these bounds are close to each other, close enough. And what is enough? Well, read about safety margins. A factor of 2 or 3 is okay, often. So it's not about 1%. Sometimes it is needed more accurately, but quite often, all we need is plus minus 30% is fantastic accuracy from engineering viewpoint. Fantastic. And the works on this started long time ago. Howard and Bousset works there probably were, well, actually, it depends on what you call the pioneer, because there was Malthus before that. But there are many works. Currently, at this time, the workhorse, something which is used in many, many situations, is the so-called background flow method, the method which was proposed by Dorin and Konstantin in 1994. The number of problems solved like this is huge. But, well, we will see more detail about this in the talk. This is the motivation. Next, well, this talk will use as a tool for explaining things first and foremost, the so-called auxiliary function method. It is a very simple, trivial thing. And the idea is very simple. Suppose we are in the following situation. dA over dt equals f of a is the system of equations, ODE, but might be PDE as well. And we are interested in the quantity which I will call phi. It is a function of a. If we substitute the solution of this equation into phi, it becomes a function of time. And then we can average it, and that will be phi bar, infinite time average. That's the quantity of interest. And moreover, we made our step back. We agreed that we actually are after two bounds, lower and upper, as in the picture. Notice, this is not the bounds for instantaneous values. Instantaneous values jump outside the range. It's not necessary, but it's the bounds for the time average. So auxiliary function idea is extremely simple. Suppose I will take just an arbitrary function v of a. And then there is a statement that if my phi of a plus f dot grad v is less than the constant b for all a, then the time average of phi is less or equal to b. Well, provided that v of a of t remains bounded on the solution. The reason is quite simple. F dot grad v is the Lie derivative of v with respect to the system. That basically means that if I calculate, like in the proof, dv over dt, it is dv over dA grad v, then dA over dt, which is equal to f. And so this f dot grad v being written like this is a function of a, but as soon as you substitute the solution a of t in this formula, it becomes dv over dt. And the infinite time average of a derivative of anything that is bounded is 0. That means that in the box, the formula, when we average it, the average of f grad v will be 0, and the result follows. So you want a bound. Just take 1v and try and see what happens. And if it happens that this expression is less than b, fine. And you can, of course, try to improve on this by changing v. You can formulate an optimization problem where, for example, for the lower bound, you will try to maximize this L over all possible auxiliary functions. That is a convex optimization problem, so it's good. Moreover, we have theorems which state that using this approach, it is possible to get as close to the actual value as you wish. Well, there are caveats here. It's not that simple, because what is the actual value is a question. And whether we can do it in practice is another question. But in principle, at least, it is there. Now, well, you can, of course, do it in a different way. You can say that we will take just this phi of t average and try to minimize it over all possible initial conditions. What happens in this case, if we formulate this optimization problem, then, well, basically its dual will be auxiliary function method, and V is actually the Lagrange multiplier. I will not go into more details there, but if you will follow the trail, you will see it. That is what we have there. And I have a very question. Okay. Yeah, fine. This is, as I said, it's just an answer to a possible question. Okay, but what you told us is like for ordinary differential equations, in particular, because when we start doing this, it is possible to use so-called polynomial optimization or sum of squares of polynomial optimization. In case when the right-hand side and the quantity of interest is polynomial, then computer-assisted technology will help us to build this V more or less automatically. And that was done. And there is a way you can reduce PDE to the same type of thing. I will not go into the more details there. It is just some walks. We are not talking about this. There will be no polynomial optimization in my talk. I'm just referring you to the line which is out there. Now, there is another reason why we can actually have a problem with having a tight bound. And that is a problem, a tight bound for what? Consider the following very simple equation. dA over dt equals A minus A cubed. It has three steady solutions, 0, -1, and +1. So if we take, for example, phi to be A squared, the question is, what is the time average of it? Well, one of these solutions, definitely we can simply take initial condition to be 0, it will remain 0. So in this case, the lower bound cannot be greater than 0. And similarly, the upper bound cannot be greater than 1. So when that theorem was formulated, that we can go as close as we wish, it is true, except that, well, the lower bound, the best possible one, will be closest to the lower possible value, to 0, while the upper will be closest to 1. And, well, that is not at all 0 difference between upper and lower bound. Okay, practically you would say, but 0 is unstable, so it does not matter in practice. It does not matter in practice, but it does matter in this formula. If you look at the equation we should satisfy, you will see that when A equals 0 or 1, then phi plus A minus A cubed, dV over dA is multiplied by 0. So whatever I do with my 0, my V, I can't change this. A problem. Moreover, that problem is actually realistic for turbulent flows. This is an example, a model system for the flow between two flat plates, like that. And this simple model, it's only 9 mode, has turbulence in it and has a lot of other things which are observed in real turbulence. And here what you can actually see is the following. The turbulence is here, this is gray area. This is a quantity of interest, which in my case is the energy dissipation rate. And for simplicity, it is multiplied by the Reynolds number. And it is plotted as a function of the Reynolds number. And you can see here on top, the horizontal line, it is a laminar flow. the dots here are various approximation, various V's, basically polynomial found numerically. And what we observe when we make the degree of the polynomial higher and higher and higher, these curves all go to one curve. And it is very far from the turbulent. But this also has so-called traveling wave solution. In this case, it's just periodic solutions. And those periodic solutions are here. And you can see that my lower bound cannot become greater than what it is here, because there is a periodic solution there. It's unstable. If I go from top, it cannot go through the laminar flow, and turbulence is in between. And well, there is another example. Kurzweil 30 work 2007. There are a couple of pictures there. It's a pipe flow, and they were looking after those traveling waves. Actually, some of the traveling waves and the laminar flow bracket the actual turbulence in such a way that whatever I do, I can't get to the real turbulence. What can be done? Well, in reality, the solutions that are unstable, they should not matter. And they do not matter in practice because there is noise in the system. So we can actually try to add noise to the system. Again, it does not switch properly. Just give me a second. Yeah, so this is it. We take the same system, we add the noise, it's standard Wiener process with, as usual. And for the statistically steady situation, we have the second line Fokker-Planck equation for the probability density. Then we play the usual game. We are saying, okay, fine, we can try to minimize phi averaged given by the formula, subject to the equation is constraint satisfied. And there is another constraint, the normalization of the probability density. We turn the handle, V is the Lagrange multiplier, and we arrive at the condition there, which is the condition of the bound. You can see that this condition is very much the same as it used to be without epsilon, plus this Laplacian. Not that much of a complication. So there was some limited research in this direction. In principle, someone needs to do something about this. It's difficult for PDE, and that will not be, again, the subject of the talk today. Again, I simply tell you, let you know that, okay, there is this problem, and there is a way to solve it, but it is very far from being solved so far. Yeah? What would be the boundary condition in V? Yes, well, basically, it turns out that you need to have kind of zero flux condition there. It is quite moderate. So if, for example, we are looking for polynomial V's, and I should say it all started with polynomial and sum of squares, then, well, if your V is a polynomial, everything is fine. It should not kind of grow too fast. But, okay, there is an issue. For example, when we start doing this in earnest, so seriously, and for example, numerically, because you can try to do numerics, that boundary condition still needs to be imposed. And there is a choice, because the total flux needs to be zero, the total integral. It's a big issue. This is a very interesting problem. For me, it is extremely interesting because the coefficient in front of Laplacian is small. And actually, we want to tend it to zero, because we are not interested in the case when the solution itself is affected by the noise. And well, all those who do asymptotical methods will immediately recognize what that is. It is a rather typical equation with a small parameter at the Laplacian. Welcome, my old friends who did asymptotics for so many years. Greg. Okay, fine. But It will not be here today. It's just a reference to this. Here is the background flow method. That's where I am interested in more. So we will be talking about the flow in a region domain omega. It might have periodic boundary conditions like a channel flow as well. Nothing changes, but it's just easier to plot it like this. Navier-Stokes equations have body force F, which is given. And we are interested in the energy dissipation rate, which is phi, in the box on top on the right. Then we introduce something which we will call the background flow, B, and required to be solenoidal and satisfy the no slip and impermeability condition on the boundary. So the same conditions that the solution is satisfied. Then we take the auxiliary functional V in a very simple form as an inner product of B and U. Those familiar will immediately recognize, wait a minute, well, actually, it should be quadratic. But the fact is, the balancing parameter is so-called, in this case, turns out to be such that it becomes exactly linear. So this is why it is a simple case. We take this auxiliary functional V, like a L2 scalar product there, and try to construct B such that phi plus dV over dt is greater than the number L. If we manage to do this, we have a bound. To see what happens there, we simply substitute this dV over dt. Well, basically, you integrate the bracket. B is constant. du over dt is given by Navier-Stokes. So the right side of the Navier-Stokes is to be multiplied by B. And this is what is written here. This is phi, the quantity we want to bound. And this is a product of B with the Navier-Stokes equation. Oops, go back. It goes forward. Yeah, well, yeah, here. So what happens here is that, well, the pressure, come on. I will have to speak without using this. So the pressure disappeared from the first line below the horizontal line there with phi, because it's a grad pressure and we take the inner product with the solenoidal one. You integrate by parts, use boundary conditions, you have it. Then you can do one more step here, and that's basically you take the viscous term, viscosity times inner product of B and Laplacian of U, and you integrate by parts again. Then what you will have will be minus nu grad B comma grad U. And this is the point where people knowing the background flow method will probably say, wait a minute, what we are going to do next is not the optimal way to find B. It's not the optimal, but it is very obvious then what's going on. So what I'm going to do, I want this expression to be greater than L. And I look at the various terms there. The energy dissipation rate itself, the first one, is clearly positive. So it's a good guy. The last one, BF, is a good guy because I can choose B whatever I want it to be as far as is possible. So it's also a good guy. The bad guys are in the middle. What I'm going to do, I will take the energy dissipation rate and separate it in two parts. One will compensate for one bad guy, another for another bad guy. This is the last line here. And in the second term, it's the third in the row here. I just completed the square. So you can immediately see what's happening here. If I will be reducing B in size, keeping viscosity the same, well, obviously, then this one will be eventually become smaller than that one. Fine. As for this one, again, it is the same because here we have U grad U and that is grad U squared and via the Poincare type inequality. In everyday life, the derivative is something like the value divided by minus the value of the boundary divided by the size of the domain. And the value of the boundary is 0. So with sufficiently small b, the second term in the last line can be guaranteed to be smaller than the first one. We have a bound. We just demonstrated that it is possible to have a bound in this way. Practically interesting question is what happens to this bound when viscosity goes to 0. In particular, that touches the first two terms. If the viscosity goes to 0, I will have to reduce b further and further down there. And therefore, the last term, which is actually what gives me the bound, b comma f, will be becoming less and less and less. So the question of whether we can keep the bound constant as the viscosity goes to 0, it's a big question. It's not that obvious. The first two terms are the problem there. Because, as I explained, if new viscosity goes down, B has to go down as well. We can integrate by parts the second term of these two to obtain the expression there, where you see now B is under the derivative, and the form of it is exactly the strain rate. When the flow is incompressible, what you have automatically is that it's not sign definite, because the diagonal terms sum to 0, so one of the eigenvalues should have different signs. And that means that it is always possible for me to find u such that this term will have negative sign, will be a bad guy, really bad guy. The solution to this, which is known at the moment, is to assume that the strain rate is 0 almost everywhere in our domain. In that case, there is no problem whatsoever there. But near the boundaries, we have a narrow layer. People doing background flow call it boundary layer, but for those who do turbulence, it's actually a viscous sublayer, not the boundary layer, which is actually much thicker. But anyway, there is a thin layer in which we can use Poincaré inequality and closeness of the bound, or rather kind of Schwarz and Poincaré, but again, intuitively very simple. We have very large value of the derivative there near the wall because the wall is closed there. And then in this thin layer, again, our spectral condition thing is satisfied. Yeah, I wrote that's what Rich told me, doing this in the case when the domain does not allow the solid body motion is difficult. And that's the problem that I am obsessed with. So fine, this is all working. In the case when the solid body motion is feeling that the background flow is almost all the solid body motion. But the shape, well, you can't, the most recent, probably the last one, solution like this is a helical pipe. You can have this kind of a screw going through it, and still it is a solid body motion. Anush Kumar, 2021 or 2, it's just fresh. So what can you do in this case? Well. Let me see. Okay, I have time, good. There are 3 ways. You can try something completely different, just say, forget all this, let's go and do something absolutely different. Or we can recollect that there was this auxiliary functional property that if you do it somehow, then you are guaranteed to have the bound as tight as you wish. So maybe we simply should go into a more and more complicated auxiliary functionals. Well, what I was doing lately was in between, the third one, because background flow method was used so many times that people accumulated a very large experience about various technical details. And so it seems desirable to use this experience, just to modify it somehow towards something entirely different, or maybe more complicated auxiliary functional towards there, but still use the experience. And maybe in this way, we will achieve what we want to achieve. So here is something different. And in order to highlight that it is something which is very different, I even flashed the title right instead of the left. Forget about the governing equations whatsoever. There are no governing equations in this slide except the last line, but don't look at it. Suppose we have the following thing. Suppose we have several functionals of our velocity field u, d1, dn. Well, I will just denote it as d. Then we have a set of functions sj, which depend on phi and d. So it is a finite dimensional Riemann space kind of thing. And we introduce the set S where these functions are non-negative. It is in the picture there. It is the region S where it is white. It is just notation, just definition. Then there is another definition. We now take a particular, any value of u, any velocity field, and calculate phi at this value of u and those d's. That gives me a point in this space. And then I look at all those points that are possible. So all possible values of this vector. The set of all possible values will be called P. And it is shaded with lines in the picture. And then one more object is a convex hull of this P. It is shown by those two straight lines on the sides, so all together. So these are just definitions of what it is. And now we have a lemma. Suppose somehow we manage to prove that the convex hull of P is inside S. A. B. Suppose that for all values of J, of all those functions of phi and 0 value of D are such that, well, this S is negative for all phi which is greater than D. It is geometrically very simple. We are saying that this point B and the axis to the right of it is all outside S. That's what this means. Then a statement. Let's now take our velocity field u and make it a function of time. No equations, just a function of time, arbitrary function of time, which runs somehow with time. But such that we can define the time average of the quantity of the quantities in question. Then, if our u tilde of t is such that the average of d is 0, then the average of phi on this trajectory, let's call it, will be less than b. Once again, no governing equations. It's just a generic statement about what happens when we have functionals around and they behave in this particular way. The last one needs to be proved, but the proof is pretty obvious because the average, time average, is a convex combination. It's a weighted sum of the values on the trajectory. And the sum of the weights is 1, and the weights are all positive. So it's convex combination. And so that basically means that our phi averaged is inside that convex hull. And that convex hull is inside S, while this part is outside. That immediately gives me the statement. Now, with this lemma, well, oh, that's the next slide. Again, it does something to me. Okay. With this lemma, I can now propose a method of proving bounds, which appears to be completely different from what we were doing. Just take these d's to be dvi over dt. We are linking back to our auxiliary function method, except that there are now many auxiliary functions, as many as you wish. Take those, construct somehow S, and you have a bound. Well, this was inspired by works of Otto and Zeiss, and Camilla is sitting there. She also participated in some of this. Yeah, there in those works, which I cite here, you will not find this. They just write integrals and do particular cases. But they all go into this framework. So we can try, we can hope that maybe we can do something like this. Unfortunately, we can't. Because, well, if you take this straight line, or in higher dimensions, a plane, supporting hyperplane if B is on the boundary, or separating hyperplane, we will immediately see what happens. We can simply take this such line by the always exists because the convex hull is convex and B is outside of the convex hull. So you can always select such a line, and as soon as you have it, you can simply take V to be linear combinations of those auxiliary functionals, and then you have the same bound using the standard auxiliary function method. So it turns out that this attempt did not work. In general, not in some particular, it's very general proof. It's the same. Okay, that was a pity, and I had to move on. So I did. Well, in what we did so far, the background flow was constant. That was independent of time. What if we try to make it time dependent? Well, basically, the statement will be there. It's only the question of how to find such time dependent auxiliary function. And we want to use the experience accumulated in using background flow method. So here's the idea. First, I step back and say, well, auxiliary background flow method will have auxiliary functionals generically of quadratic form as written here. So it is now U capital that it is a background flow. Alpha sometimes called balancing parameter, but you can also take the square and move alpha in and put it and say that alpha times U capital is my B. It's just an issue of notation. Now, if we take dV over dt, we will have what is written there, U minus U capital, comma du over dt. It is when the background flow is time independent. If it is time dependent, well, we have an extra term which contains du capital over dt. In those cases, when this inner product, U minus U capital and du over dt happens to be zero, however, my formula is exactly the same as an ordinary background flow method. And it turns out, here is the observation, that if we say that U capital is it depends on U small in a particular way, it is, the formula is written there, the meaning is quite simple. Here is our solution and varies in time somehow, and U capital also varies in time, and at every instant of time, U capital belongs to a certain set C, fixed, prescribed, and is actually the point in C that is nearest to the velocity distribution u. What happens in that case is that if we have here point u that is, oh, come on. If we have here the point, the smooth boundary, so that u is moving, then the nearest point is perpendicular to this boundary. So the inner product is 0. And if we hit the corner, then our u capital might stay there while the solution changes. But then it's du capital over dt is 0. This is geometrical interpretation. But this statement that in this case, this inner product is always 0 can be proved using only the definition of the derivative, kind of straightforward one. And then it is pretty general. So this is what I believe is a possibility. It was inspired by the work by Goodman, and David actually called my attention to this work. There, this was done, and again, it is the same story again and again. It was done there for Kuramoto-Sivashinsky in the framework of the background flow method, but without any auxiliary functionals, without any of this interpretation, just writing integrals, derivatives, and eventually you have the result. But effectively what was done here is exactly this, and it was used there to generalize the background flow method or to larger scale, more general problem. So apart from that, I don't know any applications of this idea yet. I tried, I can't. So far, again, no. Fine, there is something else, yet another idea. Helicity. In order to understand why helicity is of interest, we have to look into the question why the auxiliary functional was taken in the background flow method as what is written there, as a square of some energy. The reason is that if we take the square, we will have the norm of u squared, and then we need to take the time derivative of it. When you take the time derivative of it, you have the velocity itself there, du squared over dt. And then we multiply it with the Navier-Stokes equations, which gives us this term, dv over dt equals minus alpha u comma u grad u. That term is exactly 0. You do integration by parts, you use boundary conditions, and you find this. If it were not 0, we would be in deep trouble, because this term depends on u to power 3. So if it is positive, you just change the sign of the velocity distribution and becomes negative. And because it is cubic, increasing the magnitude of u will make it dominant. And therefore, we will not have any bounds. So using this is possible only for highest order term of v such that it is conserved by the inviscid equations. Yes, indeed, the energy is conserved by inviscid equations exactly for this reason, that this term is 0. And for three-dimensional flows, inviscid Euler equations, incompressible, have only two known conserved quantity. One is the energy, another is helicity. Conserved in the sense that in inviscid flows, if we introduce helicity, it is a scalar product of velocity and vorticity. We can write down the equation for this, and then it can be written as the time derivative equals the divergence of something. So you integrate, and if the boundary conditions are suitable, then dH capital over dt, which is the total amount of helicity in the volume, might turn out to be 0. For periodic boundary conditions, say double periodic or triple periodic boundary conditions, that is okay, it works. But when you have walls, it does not. Because if you look what the flux is, it is the expression under the integral, the last integral there in dH over dt. Well, it has pressure, it has velocity, and at the wall, it's not necessarily zero. So if we have in the situation with the boundaries, with walls, then helicity is not conserved by inviscid flow. Now comes the idea. Well, in order to do bounds, we actually don't need that. In order to do bounds, we need this quantity, this cubic term, to be zero only on such velocity fields that are the solutions of the Navier-Stokes equations. And the solution of the Navier-Stokes equation satisfies no slip condition. And that means that at least on the smooth wall, the wall normal vorticity is zero. Now, if you look at the expression there, then we have wall normal vorticity, which is zero, and wall normal velocity, that is zero. So that term turns out to be zero. Not for inviscid flows, no, for viscous flows, but that's all what we need. The cubic term to disappear in the viscous flow. And that means that, well, okay, we now take V as maybe a combination of helicity and say energy, plus linear terms, lower order terms. Yes, you can add them easily. That's how you can try to do this. Well, there is one minor problem. Galuskin-Fantuzzi doing something else on the go proved that if we have V, which gives a bound, then V itself is bounded. And helicity is not bounded. It's not sign definite. It can be positive or negative. So if we do something like this, and our functional becomes indefinite, then we can't have it bounded from below. We can't, in principle, to get the bound. That, however, is not necessarily a disaster, because if you have one V, you can always take V squared, and that will be bounded from below. Or you can go along those lines and take any function of V or elements of V. The auxiliary function of helicity written down there is written in kind of more generic form, where you can take alpha and beta to be arbitrary functions, and everything is still similar to the background flow method. So that's what I would like to do. But again, there is something here. What about a case of two-dimensional flow? When the flow is two-dimensional, helicity is exactly zero. And so adding helicity in the picture will not change anything at all. So the question is, maybe we should first see what is available for 2D flows, and surprisingly, nothing. Okay, nothing with the walls. Or at least I could not find anything with the walls. It is the same background flow method with all the same difficulties. So actually, before doing this, before playing with helicity, one should play with two-dimensional Navier-Stokes first. Fine. I started to play with it and realized that if I am on the way to making the problem easier and easier, but still such that I can solve it, maybe I should make yet another step. Well, this 2D flow is still unsteady. Question, what about steady flows? Do we have bounds for steady flows? And you look at it, and you clearly see that all those arguments with background flow, they are the same for steady and unsteady flows. In a sense, we lost the time derivative, not fully. Right-hand side of the equation is still there, so it's all somehow hidden there. But maybe, just maybe, before going even for 2D unsteady flow, we should do it for steady flow. So here is the plan. We should first try to find the bound at least for 2-dimensional steady flow. Once we are capable of doing this, we will try to extend it for the 2-dimensional unsteady flow. And once we have that, then we can move on to helicity and do it for 3-dimensional unsteady flow. And this is a very long road. I do not expect that I will see it to the end. But let's enjoy the ride. That's it. Thank you.
So thank you for this very nice talk. Are there questions? Yeah, Rich? Oh, you need this.
I'm just intrigued by your upper left box bound for 2D steady flow. How does that relate to Rayleigh-Benard convection? We'll probably be hearing a little bit more of this week.
Oh, I did not think about this because I do concentrate on the simple case of the flow alone. But as it stands right now, we actually discussed with the Charlie a lot a simple question. Is the extremal in the wall-to-wall transport problem, right? Is the extremal field always steady?
Yeah.
You probably immediately kind of look through what people do and realize that, well, I don't think so. I don't think that it is always steady, but
yeah, but what about Rayleigh-Benard after the initial bifurcation where you could just get that window where the steady rolls for the preferred solution? Can you capture that? I mean, you know, you've got steadiness in the fluid response, it's stable.
Yeah. Okay, I don't know. This realization that we actually have to go all the way down to steady flow is the outcome of me and Paolo sharing the same flat here, because we are talking for hours, and that gradually come to realization. So I did not think much about the steady flow at all.
I'd like to take some responsibility for that housing selection.
Thank you very much. And I forgot,
okay,
or not forgot.
Actually, your answer to Rich, you mentioned that together with the Charlie, you thought that maybe the steady states are the extremum. Well, in that case, I have an issue, because if they are the extremum, then in some sense, all the invariant measures, probability distributions over the attractor, are convex combination of this extremum. And therefore, they are combination of delta functions, which is, I'm not sure this is really the case.
Well, okay. When we discussed, I constructed a counterexample to this statement, but it was not a counterexample for any real flow or anything. It was just a toy model example where you have the formulation of this type, and it turns out that, well, unsteady things are more efficient than steady. So, but it does not eliminate the possibility that in a certain specific problems, which are real ones. Yeah.
Okay, do we have questions in the chat perhaps? Do we have online questions? No? Any other questions here?
Okay, I see the chat, and no, there are no questions there.
So let's thank the speaker again then.
Thank you.